Okay, so number 4 here. Now, what it looks like we're given is that we have a function f, a vector field f, and we don't know what the components are. P, Q, R. What do we know? And we've got an oriented surface. We don't know anything about the surface, other than it has a boundary curve. And all of a sudden, magically, the line integral around the boundary is supposed to be 0. Now, how could this possibly be true in general? Line integrals wouldn't be a very interesting subject if they were always 0 around every, boundary curve. So there is a critical piece of information in here that we have to take advantage of, and that is that in the statement of what this vector field is, note that this unknown function p, that's the first component, only depends on x. The second component of the vector field q, it only depends on y, and etc. Okay, so that's what we're going to use here. So let's write down what we know then. We're computing a line integral around the boundary of some surface, so we have some surface there, some sort of an orientation, and there's a boundary curve. And a line integral f dot dx. And let's use Stokes' theorem to rewrite this then as, well, it's going to be flux through the original surface of the curl of the field dot ds. And I claim that we can compute that curl actually fairly nicely. So how does that work? Well, remember the curl, it's this cross product, sort of symbolic cross product, of the del operator with PQR. But critically, P is only a function of X, Q is only a function of Y, and R is only a function of Z. So, for example, the first component of this curl is, well, let's see, the first component is the Y partial of R minus the Z partial of Q. Well, what's the Y partial of R? R only depends on Z. So that's 0. The Z partial of Q, 0. There's no Z's in there. So you get 0 minus 0. And similarly for all the rest of these, I claim that all the rest of these ends up being 0 minus 0. And so the curl is the 0 vector field. Yeah. Does that make sense? Yeah. And then therefore that's 0, and therefore the answer is 0. So this is actually not as general of a fact as you might, on first inspection you would think. Because this is only in a very special case that the components depend only on certain variables. Right. And by the way, just another point of view on this problem, another way you could rewrite this integral around the boundary of, PQR dot dx. Let me just rewrite. Remember the dx vector here. That dx vector in coordinate notation, that is dx, dy, dz. And so you could rewrite this as a sum of 3 integrals, p of x dx plus q of y dy plus r of z dz. And we've already seen in the Green's theorem section that integrals that look like this, integrals dx, where the integrand only depends on x, we already know that line integrals like this were 0 in the Green's theorem context. And so here we have you can interpret this fact here as saying that the same analogous statement is true in R3.
So in the books in the coordinate section, we're thinking of P, Q, and R all being of X, Y, Z.
Yeah, absolutely. And this is as a general rule is always the case. Well, unless otherwise indicated, P, Q, and R are always functions of all the variables. P itself will, just because it is the first component of the vector field doesn't mean that it only depends on the first component of the input vector. Yeah, no, absolutely. Yeah, they're general functions as a general rule. So again, not a very impressive result if you really think about it, because of the very restricted category of fields that we're looking at here. Yeah. Everybody happy? Okay. Let me stop the recording on this.